All right, guys, moving on. In this first time, our first unit, we're now going to talk about organic compounds and how they were created. Organic compounds are going to usually be organic molecules, so they have carbon in them, and they're important for life, and they're usually polymers, big things, of repeating chains of monomers linked together. There are 3 that are polymers by true senses, and then there's one that doesn't quite fit that. So in this case, you can see you have a chain of CH2s moving through, and that chain of CH2 as it moves through, so the CH2 is the monomer, and the big chain is the polymer. So it says, can you name 3 organic molecules that are polymers? So those 3 things are going to be your proteins, your nucleic acids like DNA and RNA, and your sugars. Those are polymers. The monomer for proteins are amino acids. The monomer for sugars are carbohydrates or simple sugars, and the monomers for nucleic acids are your nucleotides. Now, the one that says, can you name an organic molecule that is not a polymer, that's going to be your lipids. They don't fit the polymer section quite as well because they're made up of fatty acids and glycerol, so 2 things. Now, there are 2 sources for organic molecules that we need to discuss, and you decide which one you think is true, and you decide how you think you might affect or test these. So one is that all organic molecules came from space, so they would have had to come on asteroids or in the process of making the universe, or the creation of Earth itself, creation on Earth through chemical reactions. So think about it. Which one do you think is more probable? And how do you think you would treat it or test that? All right, let's learn more about it. So, organic molecules from space. The dust in our solar system from which Earth was formed was rich in organic molecules, so lots of carbon-containing molecules that came to Earth in the creation of our solar system. And then also as meteorites strike the Earth, they have hit at a lower velocity because of our high atmosphere, so then they would slow down, so they wouldn't just be completely obliviated upon landing. So there's still some that survive. We have some proof that some organic molecules do come from space because we have found in meteorites that there are some organic molecules in there. There is about 500 million pounds of organic chemicals that fall as cosmic dust to Earth each year. So we actually get quite a bit coming in from space each year. Now let's talk about from reactions. There were 2 scientists in the 1920s, Oparin and Haldane, that decided that Earth's early atmosphere would have been able to create new things, specifically because there was no oxygen. Oxygen itself is very, it's very electronegative, so it wants to bond to things, and therefore it'll break things apart. It's very corrosive. So with an oxygen-rich atmosphere, you're getting a lot of breakdown, but when you have an oxygen-poor atmosphere, you're going to get a lot of creation. So Stanley Miller, in the Miller-Urey experiment, and that's one that they love to ask you about on tests. In 1953, he built on Oparin and Haldane's reaction, and he tested it. He found a way to recreate what he considered to be the Earth's early atmosphere and environment. Within days, he was able to create 20 amino acids. So he actually produce some of the 20 amino acids. So he actually made real life things within days. So you can imagine the millions of years that we've been here that could have continued on, especially before oxygen was abundant in our atmosphere. Here's a little bit about what his experiment looked like. So he had a closed system where nothing new was coming in. Notice in all of these there's no oxygen. Hydrogen or water, methane, carbon dioxide, hydrogen gas, ammonia, and nitrogen gas. That's stuff that was in there. And he has it where there's a source of heat, and that would have come from just the sun, the UV radiation coming in. And he has water vapor that'll evaporate the oceanic compartment where the ocean would be, would evaporate, and then it would get sparked by what would have been lightning to simulate lightning. And then that would condense, and then you get the ocean again. And as that continued on, you ended up finding out that they made more and more large organic molecules like protein or amino acids, which then eventually became proteins. So when he did this and when we improved upon it, we found out that there were amino acids, sugars, lipids, and nucleotides. And there are 4 things that need to happen for a chemical evolution to occur. We need the absence of oxygen. Because oxygen breaks down things, because it's very electronegative, accepts those electrons, and we need to have it in its, we need to have very little of it so it doesn't break things down. We also need a high energy input. In this case, we have the sun for the ultraviolet radiation. There is also going to be the occasional spark from lightning. These are things that are going to input energy. You're going to need the basics of it, the carbon, the nitrogen, the actual elements, and those are going to be, they're going to have to be in the primitive oceans or in the atmosphere already. They would have had to be available to make these things come together. And you need time, because nothing big gets built quickly. It always needs time to react and reform and change. So let's test. Miller and other scientists have shown that A, simple cells can be produced in laboratory. B, amino acids and sugars can be produced from inorganic molecules. C, cells survived in the primitive atmosphere. Or D, life on Earth required material from space. Get your answer. B. B is what Stanley Miller's experiment showed, that we can actually create amino acids and sugars. Which of the following is not a condition of formation of molecules? A, a long period of time. B, inorganic micromolecules already in the system. C, presence of oxygen in the atmosphere. Or D, high energy input. Take a second, get your answer. All right. Did you say C? Because we cannot have oxygen, so that is the one that is not a good condition. Some evidence supports the theory that organic molecules in life arose deep in the oceans near hydrothermal vents. These vents will replace what variable in Miller's experiment? So specifically in the ocean, what would these hydrothermal vents produce? Atmosphere, rain, lightning, or primeval sea? And did you say lightning? Because in this case, the hydrothermal vents are creating the heat and energy. It's the energy input. Okay. Now, to make large organic molecules, they need to go through something called dehydration synthesis. So the process of removing water will make things come together and synthesize into larger molecules. So if we break them down, we got dehydration, the process of removing water. Synthesis is combining combining separate parts to make a whole. So I'm going to back up. Not that far. Sorry, guys. So dehydration synthesis, what you're going to do is you're going to take hydrogen out of one atom and a hydroxyl group out of another atom. And when those two things have been removed, you have water sitting there being removed. But then you have these two sticky ends of what lost the hydrogen and oxygen, and those things are going to want to stick together, creating a much larger molecule. I'm almost back to where I was supposed to be. Okay. Opposite of that is going to be hydrolysis, so the addition of water. Addition of water is going to break things down. Hydro meaning water, lysis meaning splitting. So in hydrolysis, if I add water, it's going to take a large molecule, it's going to separate it out into smaller ones. So that's hydrolysis. It's opposite of dehydration. So which statement is true about dehydration synthesis? One monomer loses a hydrogen atom, the other one loses a hydroxyl group. B, electrons shared between all joined monomers. C, water is formed when monomers join. D, covalent bonds are formed between monomers. Or E, all the above are true. Which one do you think is right? Did you say E? They are all true. All these things are how dehydration synthesis works. The result of dehydration synthesis can be reversed by, okay, so A, condensation, B, hydrolysis, C, polymerization, or D, adding an amino group. Get your answer. Did you say hydrolysis? If you did, you are correct. Good job. All right, so here is an example. We have a sugar plus water that gives you a smaller sugar and another smaller sugar. So is this dehydration synthesis or hydrolysis? Did I add water or did I remove water? It's hydrolysis. We added water and then we got two smaller sugars instead of one large sugar. Now this one, we have a sugar plus another sugar and we get an even larger sugar, 8 carbons now, plus water. So is this dehydration synthesis? Do we take water out? Or is it a hydrolysis? Do we add water? And did you say dehydration synthesis? You are correct. We took out water. Water was left over in the products, and we had a much larger sugar. So that's how synthesis occurs. So today we learned about the types of organic molecules, the monomers that make up those polymers, and we learned about dehydration synthesis and hydrolysis. Dehydration synthesis, making larger and taking out water. Hydrolysis, adding water and breaking things down. We will continue on with organic molecules in the next video. Let me know if you have any questions, and have a great day.